is working. Okay, good morning, everyone. Monday, yeah. We need to start this week in the best way as well, because it's the last week before spring break, which is fantastic. So let's see in the calendar. Let me close this window, otherwise I don't see anything. Here they are cleaning. I hope it's not too noisy. Cutting the grass. So today, yes, it's March 7, and we are going to keep going with the conservation of energy. And then next lecture on Friday, I'm not going to be here, so Mike is going to replace me. And then there is the spring recess. And right after the spring recess, we are going to have, let me see, one more lecture. Yes, one more lecture. So the midterms 3 is actually at the end of March. So we still have one more week before going to the midterm. Okay, perfect. After the spring break. Okay, that sounds great. So let me share now the slides. Okay, so remember this, we already saw it last Friday, and we were discussing about conservative forces and potential energy. So we were saying that the potential energy can be associated with any conservative forces and is indicated as delta U, although sometimes some books call it with a different letter, but normally it's delta U, and U final minus U initial, which is equal to minus the work done. Okay, and the gravitational gravitation potential energy is normally mgy final minus mgy initial, where y final is the final position, y initial is the initial position. We have also the potential energy for the spring, and the potential energy for the spring is minus 1/2 k x final to the square minus 1/2 k x initial to the square, where again x final and x initial are the position of the spring. So note that the friction is not a conservative force, and so is irreversible. So in this case, these potential energy are all from conservative forces, and so they are all reversible, location dependent. So let's see one example. We see a falling bottle. We have a 0.350 kilogram bottle that falls from rest from a shelf that is 1.75 meter above the floor. Find the potential energy of the bottle when the bottle is on the shelf, and find the kinetic energy of the bottle just before impact with the floor. Okay, so we know that the work, total work, is the gravitational work, which is also equal to the change in the kinetic energy, and is also equal to minus the change in the potential energy. So here we have minus the change in the potential energy means U final minus U initial. So minus mg y final minus mg y initial. And so we have that the gravitational work is equal to mg. I take it outside of the equation, and then I have y initial minus y final, because I just bring the minus inside, okay? And so at the end, we have that this quantity is simply h, okay? So is h, because we move from y final, which is h, to y initial, which is 0. And so this gives my mgh, which is u initial. So MGH is equal to also delta K, which is K final minus K initial. So K final is equal to K initial plus MGH. So which is equal to 0, because the K initial is equal to 0, plus 0.350 kilograms. G is 9.81 meter per second square times 1.75 meters, which brings to 6 joule. Okay, so find the potential energy of the bottle when the bottle is on the shelf, is this one, MGH, okay? And it doesn't give the, it doesn't make the calculation, but we know, again, M we know, G we know, and H we know that is 1.75 meter. And then find the kinetic energy of the bottle just before impact the floor is this one. So it's K final, which is equal to K initial plus MGH. Why K initial is 0? Because at the beginning, the bottle is doesn't have any velocity. So the initial velocity is 0. So this goes away. So I don't know if it's clear for you. Here is making a lot of calculation from the work energy theorem, but in the reality, you could have just even written delta G, you know which one it is, and so find that it was MGY, okay? So in this case, MGH, it would have been fine too, without making all these extra things. Are there questions or things that need to be highlighted? Let me know.
No one has questions about this in the chat. All the questions are about logistical things involving the upcoming midterms, lectures 19 through 21, 22 to 24.
Okay. So these are going to be in the next midterm. Okay, then we have another example with the Pikes Peak or bust. So we have an 82 kilogram mountain climber that is in the final stage. Let me put this down. Final stage of the ascent of Pikes Peak, which is 4,301 meters above the sea level. What is the change in gravitational potential energy as the climber gains the last 100 meters of altitude? Use U equal to 0 at sea level. And then do the same calculation with U equal to 0 at the top of the peak. So what is the change in the gravitational potential energy as the climber gains the last 100 meters of altitude? So delta U is equal to mgy final minus mgy initial. Mg, I take it outside, y final minus y initial. I know the mass of the climber, 82 kilograms. I know the constant of gravity, which is 9.81 meter per second square, so the gravitational acceleration. Then I know that it gains the last 100 meters, so means that the final position is 4,301 meter minus the previous position is 4,201 meter, but you could have already written 100 meter because this is delta y, is our delta y. So we didn't need to write it in this way. If you do the calculation, you find 80,400 joule. Okay. Now instead says do the same calculation with U equal to 0 at the top of the peak. So in this case, we write again the same equations as before, but in this case, what we have is that at the top of the peak, our U, so this one mgy final, is equal to 0 because it says that U is equal to 0 there. So we have to 0, and then we have minus 100 meter. So this brings it to 82 times 9.81, 100 meters. So as you see, is exactly the same because what changes is here we are looking at the change in the gravitational potential energy. So it really doesn't depend on the initial and final, but it depends on the change, and the change is the same. Then here we have another example. Let's see. So here it says a candy bar called the mountain bar has an energy content when metabolized of 212 calories, which means 212 kilocalories with a small c. This is equivalent to 8.87 times 10 to the 5 joule. If an 81 kilogram mountain climber eats a mountain bar and magically converts all of its energy content into gravitational potential energy, how much altitude delta y should be able to gain? Okay, so again, delta u is equal to mg y final minus mg y initial, which is mg delta y. And in this case, we are interested in delta y, which is the altitude. So delta y is equal to delta u mg. The delta u is the additional of the mountain bar, right? Of the energy provided by the mountain bar. So mountain bar here, the energy divided by 81 kilograms divided by g gives you 1,120 meter. So you see how just a little bit of food, because I would consider like a mountain bar very healthy and not that much food, it makes you do more than 1 kilometer. So, okay, this was another example. Now,
I was going to say, Veronica, it just goes to show that that assumes like 100% efficiency of dietary calories transferred into mechanical work, when in fact the human body does something far, far less. Like at best, I think we're 20% efficient in turning dietary calories into mechanical work.
Yes, because we think a lot also. So we have a lot, we chat. You know?
Yeah, and a lot of the dietary calories are simply spent keeping your body temperature up,
Yes.
right? And doing other sort of metabolic processes.
Yes, metabolic
So
processes.
maybe some of our students who are listening, I know the majority of our students are life science majors. So they've probably learned something like this in their biology courses already.
Mm-hmm. Yes, good point. Okay, then we have the speed of a falling rock. So we have a rock of 1 kilogram that is released from rest. Use both Betty's and Bill's perspective to calculate its speed just before it hits the ground. Okay, let's see Betty. So Betty is here, 1 meter. The altitude is 1 meter. And she opens her hand, and so the rock falls down. The initial velocity is equal to 0. And the final position is y final equal to 0 meter. And the final velocity is what we are looking for. So kinetic energy, K final, we are looking for the final kinetic energy, is equal as well, because the initial kinetic energy is equal to 0, right? So final kinetic energy, 1/2 mv final square, is equal to minus delta U, where delta U is gravitational potential gravitational energy final minus the initial one. So in the case of Betty, what we have that the final is equal to 0, because our y final is equal to 0. So this one goes away. So we only have the initial one. Minus and minus make a plus. So we have the mgy is equal to mgy initial. So it's 9.8 joule, because it's 1 kilogram, 1 meter, and then we have our g, right? So 9.8 joule. Then delta G final, as we said before, is 0. So if we do delta U for Betty, final minus initial comes to minus 9.8 joule, okay? And if we want to calculate the velocity, V final is equal to the square root of minus 2 delta U divided by M. So minus 2 minus 9.8 joules divided by 1 kilogram. Minus and minus becomes a plus. Then you do this calculation and you find 4.43 meter per second. Now let's look at Bill case. So in Bill case is still is a similar situation. The only change that we did here is to bring the origin up at where it was 1 meter before. Now we put the origin of our axis at 1 meter. So the rock goes from 0 meter to minus 1 meter, okay? Because the reference system has a 0 in the hands of Bill. So here we have the Y initial is 0, V initial is 0, Y final is minus 1 meter, and V final is what we are looking for. So for Bill, we have gravitational potential energy at the beginning, mgy initial, which is 0. So the opposite. Before it was 9.8 joule, and now it's 0 joule. And the final one, mgf, is equal to mgyf. So mgyf, this y is minus 1, so it brings it to minus 9.8 joule. So you see that is the opposite with respect, and here was 0, and now we have here minus 9.8. But when we do delta U final minus initial, in this case, we have final, which is minus 9.8 joules, minus initial, which is 0. So you see that delta U is exactly the same for both reference system, for both situations. And this is because what matters, as in the example of before, is the change in the gravitational potential energy. And so if we calculate the final velocity, we exactly find the same final velocity. I hope this clarifies a bit how to use the reference system and how to pass from kinetic energy to potential energy. Okay, now let's see another problem. Am I going too fast? I don't know.
Actually, Veronica, if you could go back one slide.
Yes.
There's, by the way, there's no questions about this stuff in the chat. I just wanted to point out to everyone, how would we have solved this same question way back during like week number 3 of the semester, right? We would have just used the kinematics of free fall, right? From lecture number 7.
Yes.
So that, and the interesting thing is you would have gotten the exact same final answer here. Because from free fall, you would have said, okay, V final squared is equal to V initial squared minus 2G H, if H is the total height that it falls through, right? If we start from rest, then V final would be equal to square root of 2GH, and we would have gotten exactly that same final answer. So that's good, right? Isn't that? It's good that it should agree in this particular case. But
this is a very good point, yes.
Yeah. But if you, Veronica, if you, sorry, go ahead. Go ahead.
No, and indeed you get the same results because these are two different tools and skills that you are going to learn how to solve this type of problems. And sometimes you can use only one or the other because the problem might be too difficult, but in the simple cases, yes, you can use both. But then it's requested from you during the midterm, you use this second method, because if you keep using the first method, you are not showing that you have understood this part.
Yeah,
right?
that's a very good point. And this equation here is only valid for free fall. So if students remember, free fall means that the only force acting on this rock is gravity and nothing else. So this is a very sort of special case, right, of someone just dropping a rock with no air resistance. If you look at the next slide that Dr. Bindi has, it it is an object going down a hill. So if you have an object sliding down a frictionless hill or incline, or like a roller coaster going down a track of varying slope, none of those things are free fall, right? So technically, we shouldn't use that old approach. That old approach is too limiting. But the new approach we've just learned, conservation of energy, is all good.
Yes. Yeah, and so make sure in the midterm that you use this approach, okay? Because this is what
conservation of energy.
we want to see you that you are using this. Okay, so here we have Christine runs forward with her sled at 2 meters per second. She hops into the sled at the top of a 5 meter high, very slippery slope. What is her speed at the bottom? So we use the conservation of energy because there are all conservative forces. There is no friction. So what we say is that all the energy that we have at the beginning, at the final situation, although I describe it here. So let me first maybe show this slide. So it's better. So the conservation of mechanical energy says that the energy is given by the potential energy plus kinetic energy, and that the final, using the definition and considering only conservative forces, and we saw that, for example, gravitational forces is one conservative forces, what we have is that the energy involved in the final conditions is the same of the initial condition. So, which also means that the energy is constant. So it's just changing forms, moving from kinetic to potential and from potential to kinetic, but the total energy is conserved. And this because there is no the consideration of non-conservative forces. So for example, there is no friction. Okay, so say that in a very simple way. Let's see now this problem. So they are asking what is the speed at the bottom. So here we can consider the conservation of energy because it's simpler than using other methods. So what we have is that kinetic energy initial or final. I think this is final. One is at the final position. Yes, final plus potential energy final is equal. So the total energy here in the final position is equal to the total energy in the initial position. So initial velocity, initial kinetic energy plus initial potential energy. So what we have, sorry that I have all these things in here, are 1/2. Let me remove them, actually. It's just make confusion. I'll put them back later. So what we have 1/2 m v final to the square plus mg position y final position, okay? And this is the final energy is equal to the initial energy, which is 1/2 m v naught, so initial velocity to the square plus mg y naught. So what we do, because m is everywhere, we just cross it out because we can divide both cases by m. So let me put it back. Okay, so we remove m from everywhere. So you see that it doesn't depend on the weight of Christine and the sled. It doesn't matter. And then you end up with this equation. If you want to solve it for what is asking is at the speed at the bottom. So the final velocity is the initial velocity plus 2gy final, because y final, I think that this is y initial, not y final. This is an error, right, Mike? This is y initial.
Yeah.
Yes, because y final is 0, right? So here we have that this one.
Yes. I agree.
So this one, y naught, is equal to 0, right? No, sorry. Y1 is equal to 0. Yeah, y1 is equal to 0. So this one goes away. Here we have 1/2 v1 to the square is equal to 1/2 v0 to the square. And here we have g y y initial, which is 5 meters. So yes, this comes to this equation. Okay, so we have 2 meters per second squares plus 2 times 9.80 meters per second square multiplied by the position, y0 position, which is 5 meters. And all this needs to be the square root. If you do all the calculation, it comes to 10.1 meters per second. So notice that the steepness of the slope and or whether it has bumps and dips does not matter in determining the answer. Only the change in the height and the initial speed are relevant to the answer. Okay, so if you would have used to solve this problem, if you would have used the methods that we saw in the past, they should have given you the angle, while here you don't have any angle. So for the final, when you have everything together, you will see that if you use the conservation of energy, this is such a powerful tool that you are going to use it all the time, whenever it's possible, rather than use the methods we learned in the past. So energy conservation can make kinematics problem much easier to solve. And so let's see here, just briefly, the potential and kinetic energy. In this case, initial position, we have U initial, which is mgh, because we are at a certain position h. K initial is equal to 0. The initial velocity is equal to 0, so K initial is equal to 0. In the final position, instead, we have that U final potential gravitational energy is equal to 0, and instead we have K final, which is 1/2 mv square. So as you see here, the energy was got all transferred from potential energy to kinetic energy. Okay, all of it. While in this case, we have, if we move the axis up here, what we have a kinetic energy, which is equal to 0, a potential energy, which is also equal to 0. So we have 0 initial energy, okay? And in the final position, we have K final, which is 1/2 mv square, which is for sure a positive quantity. But then we have minus mgh, okay? And so these two, the sum of these two will be equal to 0, because you need to keep the energy. And here the initial energy was 0. So this one is going to be 0, okay? So again, the conservation of mechanical energy is the sum of the kinetic plus potential energy, and the delta E, delta energy, is equal to 0. So it doesn't change. Okay. And delta K, of course, is equal to minus delta U. So the change in the kinetic energy needs to be opposite, but the same of the change in the potential energy. Okay, so conservation of energy can also be written, as you saw in the problem of before, U initial plus K initial is equal to U final plus K final. And from this, we can find another way to find the final velocity, which is a typical question that we have in our problems. Find the final velocity of the object. And so V final to the square from the conservation of energy comes out to be equal to V initial to the square minus 2G delta Y. And we saw this also in the previous problems. Okay, so for example, here, if we have this situation with these 3 people that are launching up the cup at a certain velocity and a certain Y initial and Y final. It doesn't really, at the end of the day, it doesn't really depend on the angle at which the cap is launched, does not change the result. For example, of the how much is the V final, right? And this is because as long as VI is large enough to carry the cap to the height of Y final. Okay, so these three situations, essentially, if you do the calculations, you're going to find that the energy, through the conservation of energy, that the conservation of energy is the same, which is very powerful and easier to do with respect to our kinematics, usual kinematics problems. So let's see another example similar to this one. At the end of a graduation ceremony, the graduate flings their caps into the air. Suppose that we have 0.12 kilogram cap that is thrown straight upward with a speed of 7.85 meters per second. I don't like that the per second is, let's see if we, no. Okay. And the frictional forces can be ignored. So use kinematics to find the speed of the cap when it has risen 1.18 meters above the fling point. And show that the total mechanical energy of the cap is unchanged. So here we can use the equation that I told you before. V final to the square is equal to V initial to the square plus 2 times acceleration, which we know is our G, delta Y. So if you do the calculation, we find the square root of V naught to the square initial velocity, which is our 7.85 meters per second. Exactly, this to the square, plus 2 times A, which is minus 0.81 meters per second square, plus multiplied by delta Y, which is 1.18 meter. And this brings to 6.02 meter per second. Now, and this was the first answer, number A. Now, answer number B showed that the total mechanical energy of the cap is unchanged. So we have E initial, which is U initial plus K initial, which means mgy initial plus 1/2 mv square. So mgy initial 0 is considered at the end, at the starting point, when they fling the cap. So this is 0 plus 1/2 0.120 kilograms multiplied by the velocity to the square. And so this gives you that the initial velocity is 3.70 joule. And here it says, show that the total mechanical energy of the cap is unchanged. So we need to see that the final energy is equal to the initial energy. So the final energy is U final plus K final, which is 0.120 kilogram, 9.81 meter per second square, 1.18 meters. This is the U final plus 1/2 m, the mass V to the square. So if I substitute all the numbers, I find exactly the same results, which means that delta E is equal to 0. Energy hasn't changed. So here we need to use this equation. Okay, we use this equation in the first one. The minus here is a bit confusing. Let me see. No, I cannot bring it inside. Well, it was copied somewhere. But the minus Yeah,
It's because this is the acceleration here, right?
yes.
And
Yeah.
if you choose positive y upward, then the acceleration y component is going to be equal to negative g. Yeah, that's why.
Yeah, exactly. While here is already explained with minus g. Okay. Is it clear? Am I going too fast? I see no questions, so perhaps we can keep going.
And I always like to make a picture like they've done here and define very clearly that this is the initial and that's the final,
Yes.
right? And then that follows all of our notation. So all the little subscripts that appear, right, follow that same thing.
Yes.
And I know it may seem kind of basic to make a drawing and to label the drawing, but it really does help keep like the plus and minus signs clear and things like that.
Oh, yeah, yeah. You need to do that. You need to do that because don't think that is stupid, because we also do it. And this is what we do every day. And we also do it because otherwise we make mistakes. So for you that you just have an exams about this topic, you definitely need to do it. Don't pretend to keep everything in your mind and be able to do too many tasks at the same time, because it's where you make mistakes normally. So write it down, make it simple. You don't need to make such a beautiful drawing, just, you know, a dot with the velocity going up and indicating as before in the case of this one. Yeah, so just indicating y final 0, 1, 0. This is what I need to look for, you know, something like this. It really makes a big difference. So like this with the question mark, this is provided, this is y initial, here is 0, y final is 1.18 meter. And then it's pretty easy, straightforward to do the problem. Okay, so let's see another example. So we are at the bottom of the 9th inning. A player hits a 0.15 kilogram baseball over the outfield fence. The ball leaves the bat with a speed of 36 meters per second, and a fan in the bleacher catches 7.2 meter above the point where it was hit. Here. Okay, so this is the guy with the bat that kicked the ball, and here we have a fan in the bleachers that catch it 7.2 meters above the point where it was hit. So it means that y final, y initial here is 0, y final is 7.2 meters. Neglect air resistance. What is the kinetic energy of the ball when caught? And then he's asking, what is the speed, V final, of the ball when caught? Okay, so what we have, we need to find K final. So we can use the conservation of energy and say U initial plus K initial is going to be equal to U final plus K final. Okay, so let's see here, U initial and K initial. U initial is mgy initial. Mgy initial, we say the y initial is 0 if we put our origin of the reference system where there is the bat, okay? So this is 0 plus 1/2 v initial to the square. So we have 1/2, we know the mass of the ball, and we also know the ball leaves the bat with a speed of 36 meters per second. So we also know the initial velocity. Very good. So we find the initial energy, 97 joule. Okay. In the final position, what we have, U final. U final is mgy final. So we know the mass, we know G, we know Y final is 7.2 meter above the point where was it. So 7.2 meters, okay, is Y final. And I found that is 11 joule, okay. Now you remember that if this E is also equal for the conservation of energy of U final plus K final. So if you want to find K final is equal to E minus U final, okay? So E is 97 joule minus U final, which is 11 joule, and it gets to 86 joule. Perfect. So this is the answer to the question A. Answer to the question B, then it becomes trivial because what is the speed V final of the ball when caught? And so we know how to find the final velocity from the kinetic energy, right? Kinetic energy is 1/2 mv final to the square. So V final is the square root of 2 kf divided by m. And I know now everything. So I plug my numbers and I find that it's 34 meters per second. So they actually, normally all the students love this type of problems because they are all very similar, easy. So yeah, the idea is that really you have to choose a system without friction or other losses of mechanical energy, then draw a before and after pictorial representations, define symbol that will be used in the problem, list all the no values and identify what you're trying to find. And then to solve is the mathematical representation is based on the law of the conservation of mechanical energies. And then the assess, check that your results as the correct units, is reasonable, and answer the question. Okay, so I think this is pretty much everything you need to do for the conservation of mechanical energy. And here, Mike, I don't have any more things because then we go to the momentum. So if you want to do the momentum, I leave the rest of the slides to you for the next time.
Yeah, I think that's a perfect stopping point there. And I'll pick up on Friday with momentum.
Yeah.
Yeah. Plus we're getting close to the end of our time anyway, so that's good.
Yes. Okay.
I'll just add one of the problems one of the mistakes I see the most is plugging in negative 9.80 for little g. But
Yes.
notice wherever g, like this is a good slide right here, wherever little g appears in the formulas, notice how we plug in positive 9.80 for little g, right?
Yes.
Little g is like a constant. Think of it like a physical constant, like the speed of light or something.
Yes.
Yeah.
Very good. Okay. Are there other questions or anything? If not, we finish with a few minutes in advance, which is great.
All right. So there's a question in the chat about the value to use for little g. So all of the recitation, all the things that I have programmed into Laulima use 9.80 as the value for little g. So that would be recitation, problem sets, and midterm exams. Yep.
Yeah. So it's it's a good thing to notice. Thank you.
Our textbook also uses 9.80.
Yeah.
However, other textbooks do use 9.81.
Yeah, this is from another textbook. As you see, for me is a picture. I cannot really change it. You know what I mean? So I copied from a text which used 9.81. But yeah, it's 9.80 what we use. And the same is here. So I cannot really change it. But yeah, you need to know that in our case is 9.80. Yeah, here they are all from the same text, so makes all 9.81. It's a good catch, actually, very good. Okay. Should I stop recording?
Sounds good.
Bye-bye. So yeah, next class on Friday will be, Mike will be on charge. I'll give him the slides, but he will be on charge. Thank you, everyone, and have a fantastic spring break, because I'm not going to see you before then.